Hi, this is Saurabh, and this is our demo of fast and reliable file transfer using custom file transfer protocol. So let us look at our experiment that we are looking at right here. This is the NS file that we have created for the experiment. So here we have a 100 Mbps link with 200 millisecond RTT delay and a 20% loss in the link. So the visualization looks like this. So we have a server and a client that are connected over a lossy link which is 100 Mbps and we have a 200 millisecond RTT delay and 20% loss. To help us in the demo, I've gone ahead and I've SSH'd into both the server nodes and the client nodes, and I've checked the connectivity. As you can see here, that we see around 20% packet loss when we ping. So let's go ahead and compile the code so client.c is the code that we've written for the sender, and server.c is the code that we've written for the receiver. Let's go ahead and compile the client code initially. What we're also going to do is we're going to create the 1 GB file that we're going to transfer over this lossy link. So let's create that as well. We are going to be creating the file called bigfile.txt, and we're going to fill it with random numbers, which is why we get the data from /dev/urandom, and this is the command to create 1 GB file. So let's go ahead and hit enter, and it's going to take some time to create this a file with random numbers of size 1 GB. So in the meantime, let's go to the server terminal and let's go ahead and compile that code as well. So as you can see here, a 1 GB file has been created. Let me just run across the client code that we've written so that I can show you the timestamps that we've defined for our project. So this is where we start off our get time of day. That is the just before we go ahead and send our file. So we have a get time of day right over here that starts over here, and then we go ahead and end it over here in a loop where we check if the sequence number is -1. So here we are employing negative acknowledgement, and we're going to make sure that when we receive a packet with a specific sequence number of -1, that signifies that it's the end of file transfer from the receiver, saying that he's received the entire file. So we go ahead and we calculate the get time of day over here, and then we go ahead and calculate the difference between the time from the beginning to the end, and then we go ahead and print the statistics. As you can see here, I'm printing the throughput as the file size into 8 divided by time in seconds into 10 past 6, because we're going ahead and we are going to print the throughput in the in terms of Mbps, megabits per second. This was me running through the time statistics. Let's go exit, and as you can see here, the bigfile.txt file has been created. So let's go ahead and run our server code in this case. Let's choose a port number through which we're gonna send this data. Let's assume that it's going to be like 6666, and and we go ahead and let's go ahead and run this, and the server is up and running. Similarly, let's go ahead and run the client. So to run the client, we have to mention the server, that is the other node that we need to send the data to, the port number, and the file that we would require to be sent over this lossy link. So let's go ahead and send the file, and here we see the file transfer has started. So I can give you a brief explanation of what we're doing in this code. So what we're doing is we are going to send so we're gonna be sending the data over UDP, but we know with respect to UDP we lose reliability. So for that purpose we've decided to add sequence numbers to the data that we're sending over the UDP protocol. So what we do is in the data field of the packet, we add the first 8 bytes as the sequence numbers, and we go ahead and add this to every packet of the file that we're sending. So we're breaking the we're breaking the file up into size of 1472. How we got this number is because each packet is 1500 bytes. And 20 bytes is reserved for header, for the UDP header, and we are reserving 8 bytes for the sequence number that we're setting in the data. So the rest is 1472 bytes is the data of the file that we're going to be sending. So we repeat this and we send it to the receiver. Now at the receiver end, when we receive these packets, we make note of all the sequence numbers that we're receiving, and in this way we can also make a note of the sequence numbers that are missing, that have been dropped over this lossy link. So we make a note of this, and at the end of the first transmission, that is at the end of which the sender has sent the file for the first time, we make sure that once we've gone ahead and received the first attempt from the sender, we go ahead and make a note of the sequence numbers that are missing, and we go ahead and send negative acknowledgements. So this negative acknowledgement, we go ahead and add sequence numbers into this, the ones that need to be resent by the sender, that the receiver expects to be resent by the sender. So once the sender receives this negative acknowledgement from the receiver, he is going to retransmit only these packets with the given sequence numbers mentioned in this negative acknowledgement. So once we've gone ahead and the sender has received that, he's going to go ahead and retransmit these packets, and this repeats in a loop. Now the receiver calculates the total number of bytes that he's receiving. So once this number of bytes that he's received reaches the file size, we know that we've receive the entire file. So the receiver is going to send a special packet with a sequence number of -1 to indicate that he's received the entire file, and then the server is going to close. Now the client, when he receives this, he's going to get the data and he's going to print the statistics. So as you can see here, we've gone ahead and we've completed transmission. As you can see here, the time elapsed, it took around 200 seconds to for the process to happen. So so in this case we got a throughput of 41.86 Mbps, megabits per second. As you can see here, I've also printed the number of NAT packets that were received. So there was pretty much a lot of loss in the network, but we've still gone ahead and got a good throughput of 41.86. In the report, we've shown that we've got 44.3 because when we ran it, we got a throughput of 44.3. That's the highest that we got. We made sure that we could make note of that. Now, depending on the congestion in the network, we have we get different kinds of speeds, but it's generally what we've seen is it varies between 41 Mbps to 44 Mbps, and in this case we've got 41.86. So to prove that this file was received reliably, let us run the md5 sum command. But before that, confirm that this file has been received. So as you can see here, there were only 3 files in /tmp. Now you will see an extra txt file here. As you can see here, it's the file1.txt. That's the one that's been received. To prove that it's the same file that was sent, we're going to run the md5 sum of the specific file. Go ahead and run it. Similarly, we are going to run md5 sum on the file that was sent. So in this case here, go ahead and run it. So we have to compare these two values to make sure that this is the same file. So as you can see here, if you compare both these values, you'll see that they're exactly the same. So I can confirm that file transfer was happened, and it happened reliably, and we were successful with it. I hope you enjoyed our video. We really enjoyed doing this project. Thank you for the opportunity, Professor Youngcho, and thank you for your guidance from TAU. Thank you.